name is Dave Anders. I'm also known as Purple Plague on Freenode, IRC, as well as Google+. I'm currently contracted with Texas Instruments on special OMAP 4 and OMAP 5 projects, including the Panda board. I'm also partners in a small company called Tin Can Tools. We make a lot of small tool devices such as the FlossWater and FlossWater 2 JTAG debuggers. And this presentation is a continuing series on board Bringup, and this one is UME and I2c. We're going to talk about a little bit of communication principles on what makes up asynchronous and synchronous communications, to kind of give you an idea of what I2c is and where it comes from and how it's easy to use. We're going to talk about a little bit of the drivers and software tools that are available to you under Linux, as well as some actual board Bringup use cases. Again, this is a continuing series of lectures and presentations on doing board Bringup, so that the entire group of information is geared towards someone that's being handed a brand new piece of hardware or a particular design that's not working well, or you've been given through distributors or third party. So these tools and information will give you what you need to utilize very basic techniques on doing diagnostics. So we're going to start off talking about asynchronous communication. Now, from a hardware perspective, most software developers have a general fuzzy idea of what asynchronous communication is, but it's not very clear on the actual hardware. So we're going to start off with a little bit of an introduction as to what asynchronous communication is. Simply put, it means there's no external clock signal. One of the most common and well-known asynchronous communication methods is Morse Code with the Telegraph. What we have here is a Morse key, and basically consists of a spring and two sets of contacts that allow the circuit to be either driven high or low. As an example here, I'm going to just simulate pressing the key down and showing a graph of sending a dot. We've held the key down for a specific period of time, and we can hold it down for another specific period of time and generate a dash. Most everyone in here at some time has understood or been exposed to Morse Code. So we always think of it as in dots and dashes, but in today's world of zeros and ones, we can actually simulate this with zeros and ones. So we can actually transmit digital data using Morse Code if we wanted to. Another common asynchronous protocol is RS-232. Most everyone in here has probably used RS-232 in one time or another. And in the fact that it is a UART, a universal asynchronous receiver and transmitter. So everyone's been familiar with setting up a device where you had to have your host PC at one baud rate and your device that you're connecting to at another. Just like Morse Code, you have to have an agreed upon period of length to communicate using asynchronous protocols, whether it's a dot or a dash or setting up a baud rate. So both sides that you're working with have to have accurate timing. If you're connecting to a device such as a microcontroller or a particular peripheral, that peripheral is going to have a crystal, which can be very expensive but very accurate, or you can have an oscillator, which is not as accurate but less expensive. But you can also have system clock dividers, for instance on an Atmel AVR, which might be running at 10 megahertz. You can actually divide that clock down to a specific baud rate. In this example, it's actually dividing down to 125 kbaud. If you're actually connecting to another device, it might be expecting to be 115, 200, which is an 8.5% error, meaning these two devices would not communicate with each other. So here's the problem that was not really first discovered, but it became a major problem during the early 80s of PC industry, where we had lots of small devices that needed to be connected to PCs. So we had simple peripherals such as a PS2 keyboard that needed to be connected. It needed to be extremely cheap, so it needed to have very reduced external components, which in this case means no external crystal, no external oscillator, and it needed to be able to be plugged in and working immediately. So can you imagine having a keyboard in which you had to set up the baud rate on it before you could even use it? Doesn't work too well. And that was done on a lot of designs. So it not only did it not have to have a set period length for the baud rate, but it needed to work with a wide range of frequencies because you never knew what kind of host PC at the time, whether it was working at 4 megahertz or 8 or 16. It needed to work with a wide range. So that's where synchronous communication comes into play. It actually uses a dedicated clock signal to transmit the data. And just like the Morse key with Morse code, Edison actually experimented using synchronous protocols to transmit stock quotes. So basically you had two sets of Morse keys transmitting the data. One is assigned as a clock, the other one is assigned as the data. In this example, I've just clocked in a value of 1. And each time the clock is toggled up and then down, it samples the value on the data line. In this case, I did a 0, again as a 1, and again as 0. So I'm taking a little bit of leeway on this because to make it simple for visual.
I'm saying it's edge triggered because of that case.
Yeah, it needs to be shifted just a little bit. So
it's okay. You're a software guy.
So that brings us to I2c, which can be pronounced several different ways, but that's a particular phrase that I like to use. It was developed by NXP to allow for a wide range of small, simple devices to be connected to the controller or processor that they were working with. It allows you to connect multiple units on the same bus. Intel had took the I2c specification and refined it for their own needs and actually refers to it as Asyn bus instead. Virtually every laptop and netbook out there has some sort of Asyn bus functional inside of the device. So let's talk about the physical connections of I2c. What I have here is a small serial I2c Eeprom, and this actually demonstrates 99% of the little things that you will experience with I2c. Basically, you're running with 4 main connections. You have your VCC, which is your power, your SCL, which is your clock, SDA, which is your data, and VSS, your ground. So, those are the basic ones you need in order to operate. 4 simple signals. But if you'll notice, there's actually 2 1K pull-up resistors on the data and clock lines. These are analogous to the springs in the Morse code that we were talking about. The spring basically pulls the signal back up when it's released. If the spring is too loose, it doesn't pull it back up. If it's too strong, the device cannot push it down. So if you look at the resistors for the pull-ups, you have to have them as the correct value. Too strong or too weak, the signal won't work. I2c uses an addressing method in order to talk to each of the devices on the bus. There are 2 different types that are out there. The most common is the 7-bit address. There is a 10-bit version, but it's not as widely used. So we're just going to look at the 7-bit in this case. So the upper 7 bits are the actual address, with the least significant bit actually indicating whether the command is a read or a write to the device. In this example also, the Eeprom actually has 3 pins on the device itself marked A0, A1, and A2. These are bits that allow you to either pull them high or pull them low to actually change the address of the Eeprom. In our table, you can see that A0 corresponds to the first bit of the 7-bit address. So if you change that as a pull-up resistor, that would become a 1 in that place. This allows you to take one EEPROM type and have multiple addresses available to you. Now, I2c can operate at multiple voltage levels, so anywhere from 1.2 all the way up to 5 volts is kind of a standard. So if you need to convert from your host PC, which might be, or host device that might be running at 1.8 volts, whereas your I2c device might be at 5 volts, you may need to use a level shifter in order to do that. Now there are a wide range of level shifters specifically designed for I2c, and these can be either purchased in a dip package, or companies like SparkFun actually sell the level shifter designed specifically for I2c on a breakout board. Now if you'll notice on this particular breakout board, you'll notice there are 4 resistors that on each side. Those are actually the pull-up resistors that we just discussed. So this level shifter actually includes the pull-up resistors for you. Now, when you talk about doing a design or plugging these in, you have to make sure that your SoC or device doesn't have multiple pull-up resistors in different locations. Just as we were discussing that if it's too strong, it won't work. If it's too weak, it won't work. So if you have multiple places where you place pull-up resistors, you need to check that as well. So what we're going to talk about a little bit is what is supported in the Linux kernel and other devices such as U-boot and bootloaders. So because I2c is extremely easy to set up, and most I2c controllers on SoCs are extremely easy to work with, having it supported in a bootloader is very easy to get initial support. Now, once it's booted with your bootloader, you can actually read from the I2c controller and talk to serial EEPROMs or other devices to get information. The Linux kernel has had I2c support going back all the way to the early 2.2 series. However, with newer kernels, we have a class driver that supports a wide range of controllers and features, and it's very easy to set up. And one of the things that's supported in the Linux kernel is a GPIO-based I2c controller. This basically only requires you to define 2 GPIOs on your device, and it will actually bitmain I2c for you. Now, I know that everybody in here hates the idea of GPIO bitbanging, but it's actually a great tool for cleaning up mistakes, and we'll get into that shortly. So in addition to the core drivers in the Linux kernel, we actually have an I2c character device that will allow you to access I2c devices on a bus from user space. Now, I don't recommend that doing generally for anything that you're going to write a user space driver for a device or working directly from user space for I2c, but there are specific instances when it can help you. When you're prototyping your driver or working with a new piece of hardware, I2c character device can make it very easy to debug and work with it. In addition, there is a group of tools from user space that can help you do that. That brings us to I2c Tools, and that's the exact name of the package, I2c Tools. And it consists of a wide range of small little applications that use the I2c characters device driver. And the first one, and the one that most everybody can find very useful, is I2c Detect. You basically just give it the I2c bus number, and it will scan the bus and identify addresses that are on the bus that have something available or are showing up and answering. In addition, there's also an I2c Dump command that actually works with I2c EEPROMs. You can actually dump the data from a EEPROM and see the values or cat it to a file or work with it, whatever you want to do. In addition, you can set data and get data for specific values. Now this makes it very easy to work with serial EEPROMs and other I2c devices from user space. Do you really want to do that all the time? No, but with this being specifically stated for board bring up and doing diagnostics and prototyping, it's very easy to use and work with. So let's look at some real board bring up cases. Now, one of the devices that I use on a regular basis is an I2c Gpio Expander. Now, everybody has worked with GPIOs or put a particular device on a GPIO or gotten a new board, and you needed to work with it, and you may have run out of GPIOs. This way, with I2c Gpio Expanders, you can actually add 4 to 24 inputs and outputs on an I2c bus. So you can continue adding these on with more and more as you're needing GPIOs. Most Gpio expanders also include an IRQ line that actually can connect to your device. And this provides interrupts for inputs such as buttons or data coming in from touchscreen controllers or any type of other device. In addition, most of the Gpio expanders also have built-in voltage conversion where you can actually have the I2c working on one voltage range and the GPIOs working on another. This saves you a lot of effort when you're doing white wiring and debugging so that you don't have to wire in level shifters. The Linux kernel actually has a generic PCF857X driver in the mainline kernel, and it actually supports a huge number of different manufacturers. This particular part number is a generic item that's been in existence really for about 15 years. And so there are a lot of clones of this particular Gpio expander, and it's very easy to work with. So, what can a Gpio expander do for you when you've had a mistake? Your electrical engineer, your designer has designed the board and they're missing a Gpio, or they don't have everything that you need on there to work with. You can usually take 2 GPIOs that you have existing on the design already and use the Gpio bit banging I2c driver as we discussed and actually set up an I2c controller that way. Where can you get 2 GPIOs? Most likely your board will either have a Gpio LED or a Gpio button somewhere on the design, and that's a pretty good estimate that you've got one of those 2 on the board. And you can actually steal the Gpio from one of those devices. You can set them up, and then once you've got it set up, you can actually use the Gpio expander to drive other devices at different voltage levels, or you can actually define the new GPIOs in the system and export them just like you would do any other GPIO. Once you've set up the I2c Gpio expander within the Linux kernel and you've set it up properly, the GPIOs are transparent. Basically, the I2c doesn't exist. It's abstracted for you. You only see it as a GPIO, which means any of the programs that you've written or device drivers that expect GPIOs can be linked to those particular drivers. One of the most common things that I use Gpio expanders for on a design that I'm retrofitting is to add a versioning tool. And basically what I do is set up 4 or 5 of the GPIOs as inputs, and I can actually use a resistor to pull them either high or low to give me a bit value. And this identifies the board type or board version that I'm using. It's very easy to work with, and as we discussed, if you set this up in your bootloader where you initialize the I2c, go out there and talk to the I2c Gpio expander, read the GPIOs, and you can make decisions on how to configure the design before the Linux kernel even starts to boot. So, we know we can fix things that get messed up with I2c, but we can also do a lot of debugging. When you get a new design, there are a lot of times that you want to do some debugging and working with the board in such a way that you don't want to have in a production value, production environment. So if you want to add some tools such as an I2c Gpio expander to an existing design strictly for debugging, all you need is 4 wires: power, data, clock, and ground. And this is pictured here is a small cable that you can get at any retailer, electronics retailer, and is very easy to work with. So you just put a 4-pin header on your design or solder on a header where you can get it, and you can plug it into any of your I2c devices and work with it from there. One of the things that we use on a regular basis is a Gpio button. What we have is normally the device will boot up in its existing modes as it would go out to a commercial, as a commercial product. But some conditions where I would like to have a test mode come up into a shell prompt or go into a diagnostic mode. And what I can do is have a Gpio button connected, and when I hold that button down while I'm booting, it will initiate the debug mode or the shell prompt as it goes through. Once you're done, you can disconnect this, and it's the same as before for your commercial product. Other things that are used are LEDs, of course. I use low-level LEDs for a lot of diagnostics. If you're doing something as power management development, and you've shut down the UART, shut down all your display interfaces, how do you know you actually reach the level that you're expecting? You can create lots of little different LED configurations that tell you what's actually going on with your power management at the time. Now, I2c Gpio expanders are easily prototyped. Almost every version that's on the market is available in a dip package, and you can buy these little 1-inch square boards and solder it on and have everything you need to do an I2c Gpio expander very easily. Now, if the soldering iron is not your thing and you're strictly just software note when you fear the iron, you can get breadboards that are very easy to work with. So, we've looked at some I2c Gpio expanders. One of the things that we also want to talk about is I2c Eeproms. Now, I2c Eeproms are so prevalent, I would be willing to bet that there's not a single laptop in this room that doesn't have an I2c Eeprom in it, in multiple. Your LCD panel is going to have one, your BIOS might have one, there's so many devices, your hard drive is going to have one. So they're extremely prevalent, and because they're mass-produced, they are extremely inexpensive. A typical one is going to be about 256 kilobytes. They can be write protected, so if you have some data on there that you want to prevent from being erased, you can do so. And like I said, they're extremely low cost. You can purchase actually some versions of EEPROMs for less than 1 US cent. And of course, as I just stated, you can also put multiples in the system. So lots of different devices, lots of different EEPROMs. So you can actually use EEPROMs for versioning information, and that is one of the most prevalent uses for EEPROMs. I'm sure everyone here has tried to set up a LCD panel or a DVI device or VGA with X windows at one time or another and had problems calculating the timing. Well, one of the things that's actually occurred over the last 10 years is virtually every LCD panel that you get actually has an I2c EEPROM in it. And it's actually programmed and referred to as EDID, or Extended Display Identification Data. So every HDMI that you work with, every DVI, and virtually every VGA that you work with actually has I2c on it that reads the timing information. So they actually have a complete standardized format that the information is stored in the EEPROM. So because every LCD panel has this, the prices on these and the standardization is out there. I mean, there's tons of them that are available. Now, a good example of this is BeagleBone cakes. They actually use a 256K EEPROM to identify each cake that's on the board, or can be used with the board. They've gone through, and this has gone through several different revisions over the years with the original Beagle board, with accessories, and learning how to format the data and use it properly. And over the years, it has become fairly stable and very widely used for all of their products. So each board you plug in will have an EEPROM that identifies that board's characteristics. It'll identify the part and board identification in lots of different ID board-specific information. This is a small clip of the format that you would see inside an I2c EEPROM or a BeagleBone cake. You have a header identification, the format version, the board name, the manufacturer, part number, and you can actually use this same type of format with your board designs. It's open and available to anyone, and it is so robust and well tested that this doesn't make sense not to use that type of design when you're doing new boards. So, what can we do with EEPROMs for debugging? It's a read and write material, but there are a lot of things that you can do with it. Just like the I2c Gpio Expander, all you need is 4 wires: power, data, clock, and ground. So, when I get a new design that I need to test, I want to do automated cycle testing. I'll set up the board to boot up, do a series of tests, and reboot. And I may set this up 6 or 7 of the boards all together and leave them running over the entire weekend. So what happens when the board fails? Or if a design failure starts cropping up, or it just completely quits working altogether? So during the testing, I'm actually writing each cycle value and whether it passed or failed to an EEPROM. So if the board completely blows up, let's say the power or the SoC on that particular board stops working, I can take that serial EEPROM, plug it into another device, and read the last time it cycled and passed, or what was happening on the testing before it failed. I also collect a lot of board interaction data. Lots of times what I'll collect is insertions and removals of USB devices, whether it's a thumb drive or USB hard drive. I'll also collect data on how many times an HDMI interface has been plugged in, how long it was plugged in. So there's a lot of ways to collect data and use it. And again, the best thing about it is if the device has a catastrophic failure, you can still take that chip and put it on another device and read it. And just like on the Gpio Expander where we talked about using buttons to boot into separate modes, we can actually use the serial I2c EEPROM to do the same thing. In an Android format, for instance, we can actually set the EEPROM to tell it to boot into fast boot every time, or to boot automatically in ADB. So there's a lot of different options that you can use, and it's very, very versatile. And I can't emphasize enough that these are so simple to use, it just doesn't make any sense not to use them in your debugging process. And again, they're easily used, whether you want to use it on a breakout board and solder it down, or use it in a breadboard. So, in conclusion and kind of summary here, we talked about some communication principles, kind of introduction into asynchronous communication versus synchronous communication. We've also talked about what's available in the Linux environment, whether it's kernel or user space and the tools that go along with it. And we've also talked about some board bring-up use cases. And because board bring-up is one of the least documented environments, you can't really go out and buy a really good book that tells you how to do board bring-up. Sharing some of these basic tips and understanding with everybody, because sooner or later you're going to be handed a board either A, is not working well, or B, has never even been powered on. So I hope some of these tools and tips and tricks will help you on that. My other presentations are available online as well, so if you want to look at LCDs or other devices, board bring up, I have those available. Questions? Yes, sir.
What about multi-master for the software I2c?
The question is multi-master for I2c. And to be honest, I dislike using multi-master altogether, and I try to avoid it. I'm a firm believer of KISS principle, keep it simple, stupid. And in these cases, when you're doing a board bring-up, you don't need to introduce more trouble than you're trying to fix in the start with. So although it works well in a production environment and planning larger systems and working with, for my cases, board bring up, I try to keep things extremely simple, one master, and usually I don't put more than 4 slave devices on one bus at a time.
Say when you've got a dead board, what sort of external device do you use to read the I2c bus on there?
I'm sorry, can you repeat?
Say you've got a board that's died,
Right.
and you want to read the E2prom on that board, and so you have to connect an external, say, USB to I2c device. What particular models have you used?
The question is, based on my reference there about using EEPROMs for board Bringup, if the board has failed, how do you read the EEPROM on your host PC or another target? Most of the time, I use either one or two things. One, I make sure that the EEPROM is actually on a breakout board that I can unplug and then plug it into another identical device, or there are a wide range of USB to GPIO type devices such as the FTDI FT2232, which actually has USB to I2c on board, and you can actually use this through libUSB, and there's quite an extensive range of libraries that allow you to do that. Once you've set it up with the USB to I2c device, all your standard tools like I2c Dump and I2c Detect work perfectly fine.
Kind of related to that, have you do very much where you do an externally powered connection to the I2c on board to try and bring it alive?
So the question is there ever a condition where you want to externally power the I2c? Yes, you can actually do that. The best way to do that is actually utilizing a level shifter so that you have the I2c device basically isolated. So you have the power on one side for the host device and the power on the other side for the I2c. So yes, the best way to do that is through an I2c level translator, even if you're going from the same level. You have 1.8 on one side and 1.8 on the other. That's the best way to protect it and keep it isolated.
Yeah, it's a good idea because I've had the problem where we did that and we were parasitically powering the CPU.
Any other questions?
What about SPI? Because you mentioned that you can use Eeprom to store, to track data. What not many people know that there are the FRAMs. That they have, for example, 40 megahertz to write.
Normally, the question is, what I've referenced I2c on this for storing data and everything, and the question is, well, what about SPI? In this particular context, there are a couple things. First of all, SPI tends to be a little bit more difficult to set up on controller basis, whether it's in bootloader or something else. The second is it actually requires more wires, and when I'm debugging, I don't want to solder more wires. I want to keep it down as minimal as possible. SPI can be bit banged as well as I2c, but again, it needs more GPIOs, and you have to steal more GPIOs from other places. So yes, it can be used, but in my context, I want to try to keep it everything as simple as possible and as less damage to the board when I'm actually trying to bring it up.
You could bit bang I2c to Gpio Expander and then use that to bit bang SPI.
and because that the GPIOs are transparent once they're set up, all of that works very well. And in fact, I have had a specific condition where I had an I2c controller talking to an I2c Gpio Expander, and that had two GPIOs that were configured as I2c bitbang connected to another I2c Gpio controller which actually had the GPIO. So that's how robust the Linux drivers are and how well they're written, that you can daisy chain these in loops all day long and it just simply works. It was pretty slow. I think I actually clocked it around 2 megahertz, so it wasn't too bad. I'm sorry, not 2 megahertz, 2 kilohertz. Sorry.
Can you close the loop?
I haven't tried that one yet.
Was Spock impressed?
Yeah. Ben?
Any recommendations on analyzers for I2c buses?
Actually, yes. There's an open source project called SIGROC. They have a huge number of tools that are available. There's OpenLogic Sniffer. These are all low-cost designs. And if you actually go to my reference page, I actually have a link to several different logic analyzers. And most of them that can do I2c sniffing are less than $50, so it's very affordable to work with.
You ever experienced I2c bus getting stuck, and what are your techniques for getting it unstuck?
Yes, I do see I2c buses. The question is, do I ever see I2c bus get stuck, and what do I do to resolve that? In most cases, it is either the pull-up resistors are not correct. Somewhere down the line, too much or too little has been put on the bus. A lot of times, level shifters actually include pull-up resistors internal to the device, and if you're not careful looking at the data sheet and don't realize that, you can create a lot of problems on the system. But the easiest thing that I've worked with to debug all of that is just a good dual trace scope and actually look at the signals. And that's kind of why I did an introduction to synchronous versus asynchronous, to get an idea of what the signal might look like if you were to actually look at it on a scope. And so you also have to take in, for this presentation, I tried to keep things as simple to give you a good introduction, but there are so many different types of things that can go wrong, but if you sit down and work through them one step at a time, and because the I2c has been around so long, there is so many how-tos and good reference material that it just makes good sense to use it because it's such a good device.
The Linux, I've never looked into the Linux BitBang I2c driver, but does it actually implement the fact that on I2c the slave device can hold clock low?
Actually,
Extend the cycle?
yeah, that's called clock stretching.
Yeah.
I don't believe the Gpio BitBang supports that. I have seen some patches out on the mailing list, but I don't think it's actually been accepted.
Have you ever come across devices that actually do that?
I have actually, and it's actually becoming more prevalent with more and more in-vehicle entertainment systems that are coming where we have displays in the headrest in the back of your vehicle where you can watch TV or videos provided by a computer that might be somewhere else in the car. They actually have what's called flat panel link that encodes I2c over the signal. And in order for that to work properly, clock stretching must be supported. So a touchscreen controller on the back of your car where the computer's in the front, you have to support the clock stretching or it just simply won't work.
Okay. Just on that clock stretching stuff, what I was talking about with this bus getting stuck, if you reset the master while it's in the middle of a cycle, the slave can be expecting the master to be doing something and can actually be holding the bus down.
Correct.
So if you reset everything, it works. But you can also give the master a couple of clocks blindly until it unsticks the slave, and that's another way to.
Well, thank you all for attending. I appreciate it. And again, if you have any questions, feel free to ask me. Thank you.